think we can get started with this session. Welcome everyone. My name is David Garcia. I will be chairing the session. We have 3 speakers this afternoon. Remember that each talk is half an hour, and then we have 5 minutes questions at the end of each talk. And then we don't have any break in this session, so we will have a colloquium at the end of the session where you can ask your questions to the speakers directly. Remember that you can post your questions to the questions and answer chat, and you will also get the link to this colloquium in the chats. The first speaker is Nurit Avraham. She's a researcher associate at the Department of Condensed Matter Physics in the Weizmann Institute. Her research interest focuses on the electronic properties of topological materials, and they study these properties using scanning, tunneling, and microscope. Nurit, whenever you want, you are welcome to start.
So thank you, David, for the introduction. And I'd like to thank the organizer for inviting me to this great conference. So today I'm going to talk about scanning tunneling microscopy measurement we've been doing on the transition metal dichalcogenide 4Hb tantalum disulfide, in which we have seen signature of topological nodal-point superconductivity on the material surface. In particular, we have seen boundary modes that their properties signify the existence of nodal point topological superconductivity on the surface. So before starting, let me present the people that's responsible for this work. So on the STM part, it's Abay Kumar-Nayak, together with Avraham Steinbock, Yotam Roet, and Chaim Weidenkopf. In collaboration with Jun Ku and Bing Gayan, who did the DFT calculation, and in collaboration with Gilad Margalit and Yuval Oreg and Gregory Fitt that did the theory for this work, and in collaboration with Irena Feldman, Davio Amoalem, and Amit Kanigel from the Technion that provided the samples and many interesting discussions. So, what happened? I just cannot change the slide. Oh, okay, so the outline will be as follows. I'll start with some general information about 4Hb tantalum disulfide and the CDW configuration that we see on top of it. And then I'll focus on the 1H layer termination of the tantalum disulfide, and I'll show the general properties of the superconductivity state that we observe on this surface. We'll see that it's a gapless superconductivity. I'll show that we see subgap peaks on vortices, presumably zero bias Majorana peaks. And then I'll focus on the main topological signature of the superconductivity, which will be the boundary modes that we see on different boundary of the surface, which will be physical boundaries. Here I will distinguish between 2 types of boundary. One will be the physical boundary of the 1H layer, and one will be a boundary that distinguishes between 2 regions of the same 1H layer. On one of them, the 1H will be encapsulated symmetrically from top and bottom by 1T layers, and on the other, there will be asymmetric encapsulation only from the top, and we will see that we see also boundary in between. I'll explain and show why we understand for the existence of the boundary of the edge mode at this boundary. And finally, I'll describe the theoretical model that captured all our observation. And this theoretical model actually was extended in a separate paper by Gilad Margalit, Erzberg, and Yuval Oreg, and it appeared already just recently on the archive. So let's begin. So this is the structure of the 4Hb tantalum disulfide. So in general, we know that van der Waals material provide a great platform to tune electronic properties and to engineer novel phenomena. And particularly interesting is this family of TMDs that already before even stacking them provide fascinating correlated phenomena. So 4HB is an alternating stacking of the 1T and the 1H tantalum disulfide polytypes. And so this is the structure. And the main difference between the 1T and the 1H is that the layers of the sulfide here, in the case of the 1T, they are aligned vertically one on top of the other, giving rise to this top view. And on the 1T, they are rotated one with respect to another by 60 degrees and giving rise to this top view. As for their electronic properties, so the 1T have been shown to exhibit different kind of CDW in the very low, in a low temperature. It shows commensurate CDW in the form of Star of David that are commensurate with the crystal structure that are shown here in this cartoon, where 13 tantalum atoms are bunched together to create this form of Star of David. And these have been shown by many groups with scanning tunneling microscopy. And it is known for showing multi-insulating behavior with no magnetic order. And recently, the ground state have been suggested to form a quantum spin liquid. And then we have the 1H layer, which is known for its Ising superconductivity. In the bulk form, the TC is about 0.7 Kelvin, and in the thin limit, the TC was shown to increase to around 3 Kelvin, and in this form of 4HB tantalum disulfide, it was found to be 2.7 Kelvin. So this form of 4HB is an extremely interesting stacking, and it's interesting to see how these phenomena are affected when they are coupled in this stack. So in the bilayer limit, an heterostructure of the 1T tantalum disulfide and the 1H have been investigated, and it was shown that a condo effect was observed, where the magnetic moment that are associated with the Star of David are screened by the metallic conduction electron of the 1H layer below, and it shows also heavy fermion gap. And in the bulk form, MuSR measurement shown an increase in the MuSR signal onset exactly at the TC where superconductivity onsetting, suggesting time reversal symmetry broken, suggesting the existence of chiral topological superconductivity. So motivated by this work, we have decided to investigate the topological superconductivity on the atomic scale using scanning tunneling microscopy. So what we do is the following: we take a sample of 4HB tantalum disulfide, we put them in our system in UHV condition, and we cleave the sample to expose nice surfaces and clean surfaces that can be measured using scanning tunneling microscopy, and we bring an atomically sharp tip to close proximity with the sample surface. So since this and we measure the tunneling current between the tip and the sample, and since this tunneling current is extremely sensitive to the distance between the tip and the surface, we can measure the topography of the sample down to atomic resolution. We can also measure the derivative of the current with respect to the bias voltage, and this gives us a measure of the density of state at the location of the tip. Of course, we can scan the tip and take line cuts and map and measure the density of state as a function of location and as a function of energy. So here I put two configurations of topography that we observed on the surface, just to show the different configuration. We can measure just the 1H termination, the 1T termination. We can see steppages when the 1H is above, and also steppages when the 1T is above. And we can see all sorts of direction, which allows us to characterize and see the properties of these the boundary modes that we will see on the these steppages. Okay, so let's focus on this topography where we see the 1H layer on top of this 1T layer, and let's expect the periodic patterns that we see here. This is the charge density wave. This is the 1T region. So let's take a better resolution. Here you see very clearly the Star of David CDW, and we also see the atomic structure. If we take a Fourier transform, we can clearly identify the peaks. These very bright peaks are the peaks of the CDW, and these are the peaks that correspond to the atomic structure. And we can do the same also on the 1H layer. We see very similar topography. However, the CDW that are seen here are not CDW that correspond to the 1H layer, but are CDW that are imprinted due to the proximity to the 1T layer below. So these are the CDW that are imprinted from the 1T layer. So if we take a Fourier transform, we can again recognize the atomic Bragg peak, and we can also recognize the charge density wave that are imprinted due to the proximity to the 1T layer below. And if we look very carefully around here, we see another set of peak. This is the peak of charge density wave that are typical to the 1H layer itself. So the 1H consists hosts superimposed CDW that are related both to the 1H layer and the one that are imprinted by the 1T layer below. So let's also look on the spectrum. So this is a line cut that cross both layers, and let's see the average spectrum that are measured along this line cut. So this is the spectrum, the DIDV, the density of state as a function of energy. This is the one that is measured on the 1H layer. We see a metallic behavior throughout the energy range, and this is the 1T spectrum, which show this insulating behavior below the Fermi energy. So now let's cool the system and inspect the superconductivity that we observe on the 1H termination. So this is the spectrum in the normal state. And now let's focus here around the Fermi energy, and let's see what happens when we cool the system. We see clearly the superconducting gap develop around, see the difference in scale between here and here. So this is the superconducting gap that develops around the Fermi energy. If we hit the system above 3.5 Kelvin, this superconducting gap disappears. And if we also apply magnetic field of 1 Tesla, again, this superconducting gap disappears. So we were able to fit this superconducting gap by a standard BCS fit, but we have to add an offset because one of the things that should be noticed here that we don't have a gap superconducting gap, but we have a residual density of state at the zero energy, and we extracted a gap of 0.44 millivolt. From now on, I also will refer to the gap by the distance between the coherence peak and the zero energy that we can extract from here. And we have shown that this behaves spatially and exactly as the gap that we extract by the BCS fit and the offset. So let's see the spatial behavior of this gap. Let's take a line cut along this region on the 1H termination. Here is the line cut. This is the energy. This is the location axis. And we see that the gap remains robust and uniform along this line across the 1H termination. The next thing we did is applied magnetic field and examine the formation of vortices on the 1H termination. Here we see a very nice Abrikosov lattice indicating that the pinning is weak in these materials. And among these nice vortices, we see speckles where the density of state increases by about 10%. on these impurities, we extracted coherence lengths from the decay of these vortices of 21 nanometer. Now let's inspect the structure of a single vortex by taking a line cut along this vortex. Here you can see the energy range, and this is the location along this cut. If we take a profile around here, just far away from the center, we see the typical superconducting gap. And if we take a cut just at the middle, we see this peak at the center of the vortex. We fit this peak by a Gaussian fit and got a width of 0.25 MeV, which corresponds to 1.7 Kelvin, which is higher than the temperature we measuring at. But it turns out that this peak can also originate from a CDGN state, Caroli-Dugen matricon state, and turns out that the Levin spacing between these CDGN state doesn't allow us to distinguish, for example, the existence of Majorana peak from the existence of these CDGN state. So this could be a signature for first signature for the topological, but it's by itself not enough to indicate topological superconductivity. So the next thing we did is we went to examine what happened on the boundary of the 1H steppage termination with the aim to look for boundary modes. So here you see a topography of the 1H layer. This is on top the 1H layer, and this is the 1T layer at the bottom. And let's inspect what happens just at the edge. So first of all, let's look on the superconductivity spectrum far away from the edge. So this is the one that I've shown you before, with the which we can fit by a BCS plus an offset. And let's see what happens when we come close to the edge. So we see a huge increase in the density of state at the zero energy, and we see a very slight reduction in the gap that is shown around here. And when we try to fit it again by a BCS plus an offset and account for this small reduction, it doesn't account for the huge increase of that we see in the zero bias. And we were able to fit it nicely when we added an additional density of state in the form of this Gaussian form, which indicates for the additional density of state that exists here on the surface and cannot be accounted just by the reduction of the superconducting gap that we see on the surface. So now let's see the evolution of this gap when we go from far away to very close to the edge. And let's go along this line cut. So here you see the superconducting gap far away, and we see that it remains constant, and it just decreases very slightly at the last very few nanometer close to the edge. So let's see the increase of the density of state at the zero bias. So you can see it over here. So what you see here is the size of the gap along this line, and also the increase of the density of state as we go from this point to the point just at the edge. So we see that the gap as extracted from the coherence peak remains constant all the way down to the last few nanometer, and only at the last few nanometer it reduces a bit, whereas the density of state at the zero bias start to increase at a much larger scale and reach a very high density just at the edge, signifying the existence of this boundary mode at the edge. and we extracted a localization length just by fitting an exponential fit of 18 nanometer of this boundary mode that exists on the edge. We can also trace the dispersion of this edge mode as a function of energy just by taking this line cut at different energy, and we can see that the localization length remains constant throughout the gap and only start to go to decrease where at energies where the superconducting gap decreases. And let's see it also in 2 dimensions. So this is the IDV map of this region, which clearly show the boundary mode that is localized at the boundary of the 1H termination. And when we apply a magnetic field, we see that this boundary mode disappears. So what I was showing now is that just at the termination of the 1H, we see a boundary mode that exists and is localized to the 1H termination. So now I want to inspect another boundary mode that exists on a different step edge, and this is the step edge of the 1T termination. And we will see a boundary mode just at the bottom of this step edge. And actually this boundary mode distinguish these 2 regions of the 1H termination, whereas in one region, the 1H is encapsulated between these 2 layers of the 1T. So we have a symmetric configuration, whereas on the right, we see 1H layer, which is encapsulated by the 1T only from the bottom. And this gives different configuration where the mirror symmetry is different along the perpendicular direction out of plane. So this is the topography. Now we see the 1T layer is above the 1H, and we see this crater. So first of all, we applied magnetic field at low temperature, and we were able to again see the superconductivity, the Abrikosov vortex lattice. And interestingly, when we go to the edge, we see a vortex, a partial vortex that continues down in the 1H layer below the 1T layer that covers it, which means that the superconductivity continues both in the exposed layer, and it continues into the 1H layer that is covered by this 1T layer above. So now we want to see what happens on this boundary. So let's go to this region where we don't see, with no magnetic field, and let's see what happens on this boundary. So this is an enlarged, the IDV of this region that we see around here. So this is the 1T layer, and this is the 1H crater, and we clearly see the boundary mode run along this mode. And interestingly, we see that this boundary mode is anisotropic. We see that the localization length around here is much shorter than the localization length that we see around here. So we were able also to extract them different direction. We can see, as I said at the beginning, we see a different type of orientation. So we see that this crystallographic orientation is the zigzag direction, and this is non-crystallographic direction, but it is aligned with the direction of the CDW superstructure. And when we extract the localization length along these 2 directions, we see that the localization length along the zigzag direction is 12 nanometer, whereas the localization length along the perpendicular to the CDW direction is only 18 nanometer. Okay, and as I told you, we have these different regions with different orientations, and we measured many such topographies with many steppages, So I won't go in details to all of them, but all of them show this edge mode localized at the boundaries, and some of these steppages are such that 1T is above and the other, the 1H is above. And in some of them, we have the zigzag configuration. In some of them, we have the CDW configuration. And remarkably, when we look on the localization length, this is a kind of a summary of all those steppages that we have measured. We see a remarkable consistency of the localization length as a function of the direction. So we see that all the CDW direction, whether they are of this configuration and the other or the other configuration, show the same localization length, more or less, of 18 nanometer, whereas the other direction show a localization length which is shorter. This is the zigzag direction where we measured 13 nanometer. So just to summarize what we have seen so far, we see that on the 1H layer, we have a superconducting behavior with gapless behavior. We see that the vortices host zero bias peak. And then we found out that the 1H termination show a boundary mode that is localized to the physical termination of the 1H. And we also found that we have a boundary mode that distinguish different region of the 1H, where in one region the 1H is encapsulated by layers of 1T from both sides, and in the other it's a non-symmetric encapsulation. So let me just give some more insight. We did some DFT calculation to understand the difference between these two regions, and it turns out that that when we stack 1T and 1T layer, bring them into proximity, due to the difference in work function, then charge is transferring from the 1T to the 1H layer. And in the symmetric configuration, it happens from both sides. So there is no total polarization, but actually this charge transfer is also the origin for the imprinted CDW that we see on the 1H layer, the one that are belong to the 1T configuration. But when we do the same thing for the non-symmetric configuration, then we have a non-symmetric charge transferring, which gives rise to polarization just at the interface with the 1H, between the 1H and the 1T. And this is actually can be considered also as a Rashba spin orbit coupling, because it gives rise to a perpendicular electric field, which behave as a Rashba term just at the interface. And this what breaks the mirror symmetry in this region, the mirror symmetry perpendicular to the plane of the 1H layer. So now let me try to describe the theoretical model that actually takes all those ingredients into account and nicely captured all the observation that we have seen so far. So in the model, the 2D monolayer of the 1H tantalum disulfide is modeled by a triangular lattice with a minimal set of orbitals that you can see around here. And the resulting band structure, which corresponds to this tight binding model, is shown around here. This is the 2D band structure, and here is the dispersion along this line that goes from gamma K to M to gamma. Now, the question is what type of superconductivity can form in this configuration. And this really depends on the symmetries of the system. So it turns out that if mirror symmetry exists, then we can have only the trivial S-wave pairing, and the system can exhibit only standard S-wave superconductivity. However, if the mirror symmetry is breaking, just as we see on the surface, on the exposed surface of the 1H termination, then both the S-wave pairing and also topological pairing, which couple inter-orbital states with different orbits, but with the same spin, is allowed. And now the topological state of the topological nature of the superconductivity will be determined by the relative strengths of the standard S-wave pairing and the topological pairing. So it turns out that if the delta S is dominating, then we'll see superconducting S-wave superconducting up throughout the Brillouin zone. However, if delta X and delta S become comparable, then the superconducting gap suppresses around this region where we see this crossing. And when delta X becomes dominating, then nodal point structure is developed around these regions. And in 3D, this is the way it forms. So we see two nodal points that are forming at all these three directions. So here we see again the two-dimensional Brillouin zone where these points marking the location of these nodal points that are formed when the interorbital pairing is dominating. Okay, so now I'd like to show that this configuration actually is expected to show the anisotropy that we see in our experiment, because whenever we have these nodal points in all these 6 directions, this would give rise to those edge modes that we measured on the edges. So let's focus, for example, on this orientation. So we have all these nodal points in all these 6 equivalent directions. So let's expect what will happen on the zigzag direction, which is shown around here. So in this case, these two Weyl points will overlap with the other projected Weyl points, and we expect to see edge modes, 2 edge modes that are contributed by these 2 pairs of nodal points that span the momentum interval between the location of the nodal point and disperse as shown around here. And let's take different orientation where, for example, these
we have just a little bit more, but we should go to the questions as soon as you want.
Okay, so I'll just one more sentence. So in this configuration, we have different projection, and in this configuration, for example, when we have only slightly overlap, we have a combined configuration of such kind of edge mode and dispersing edge mode, and this is also the calculation. And this is a calculated localization length, indeed, that show this anisotropy, which is consistent with what we have measured. So let me put this summary and let's go to the questions.
Great, fantastic. Thanks a lot, Nurit. We have, I want to remember everyone that you can post your question to the question and answer chat. We have so far 3 questions.
Yes.
One from Divya Ravat. Is the magnetic field altering or giving rise to some variations in the CDW transition in the 1T phase with superconductivity?
Again, if the magnetic field affects the CDW
transition,
like when the CDW becomes commensurate and this kind of transition.
Well,
so
yeah.
So not that. No.
Maybe we can, if it's not clear, we can leave it for the colloquium.
Yes.
We have another question by Bahit Satrari. These materials are type 2 semiconductors. So how do you apply how can you apply the BCS theory to them?
So the way we understand it is that the pairing is BCS plus. So according to our understanding, the pairing that we have here is BCS plus this inter-orbital pairing, and the idea is that we wanted to show that the additional density of state that we observe on the edge mode cannot be accounted by the reduction of the gap that we see near the surface.
Okay, so then we have another question by Sebastian Diaz. How could you probe the chirality of the 1D edge modes, perhaps using two STM tips?
So with this measurement, first of all, the system is time reversal symmetric, so we don't expect a chiral edge mode at the edges. But anyway, in this kind of measurement, it's hard to, we cannot distinguish the chirality. Maybe with the spin polarized STM, we can detect these, the chirality, but so far we didn't measure the chirality, and in general, this is a time reversal symmetric system.
We have a question by Tanais Timo.
Yes, in systems like superconductor normal junctions, typically you obtain coherent Andreev reflection and zero conductance peaks. But would you exclude this kind of coherent Andreev reflection in your edge modes there?
And they should, the question is whether they should show all these anisotropic properties that we have seen here. So we didn't specifically distinguish them, but the properties that this edge mode, and also one thing is that we see this edge mode that exists on kind of a non-boundary, just on the 1H termination, where there is kind of a virtual boundary. It's not a physical boundary of the layer. It's just a boundary which separates different regions with different mirror symmetry properties.
Okay, thank you.
We have time maybe for a final question. How do you prepare the alternative stacking? This is a question by Chao.
How we grow this, so the growth was not done by ours, it was done by Amit Kanegel, and it turns out that it's quite difficult to grow these samples, and they have to add some selenium in order to stabilize the compound, but we are not the expert in growing these materials.
Okay. Thanks a lot, Nurit, for your presentation. We will have time at the end of this session to discuss with the speakers. So you will get the link in the chat. Now we will move to the next speaker. Maybe Nurit, if you can stop sharing your presentation.
Yeah.
Thank you.